Anza is the company behind all of the validator code base that is on the Solana network today. First, how do you define what is SVM?
Technically speaking, the SVM is the state transition function.
For developers who are new to crypto or people who are coming from the EVM side of the world, how should they understand SVM?
We do have actually an instruction set architecture that lays out what all the opcodes of the VM are. We do have that.
SVM execution environment is actually the eBPF, and then we have special opcodes on top of that. Why eBPF was chosen?
I mean, the core reason it was just easier to do. So, like,
Do you have any specific repositories that you recommend people look at when you have both these set of tests?
I would say the Solana program org has a lot of.
How are people using SVM APIs?
Well, you can build a state channel with.
Hello, welcome to another episode of the OnlyDevs podcast. Today is a special episode. We have Joe, who is an engineer at Anza, and Anza is the company behind all of the validator code base that is on the Solana network today. And welcome to the podcast, Joe.
Thanks, guys. Thanks for having me.
This is a question that we ask everyone. It's a standard in the podcast. What pulled you into crypto?
So, like, for me, this was like 2019, maybe. Or no, I'm sorry, maybe like a little after 2020, like a little bit towards the end of the pandemic. I was working at a bank and I had actually gotten a software engineering job, like the first job that I had, because I was doing something totally different before. I was like basically mowing lawns and like just doing stuff like that, like snow plowing. And I was like getting into coding and I got my first job at a bank. And I quickly realized that like a lot of people were kind of like complacent. And I was really more interested in working on like some cutting edge stuff and like really crazy, interesting, cool tech. And I went to some of these like conferences, like permissionless and like Solana hacker houses and stuff like that. And I was like felt like I was like having an affair. Like I was like sneaking out and like going to these conferences on the weekend and like coming back to work on Monday. And eventually I was just like, I figured this is probably where I was going to end up. And then I met some cool people from Foundation down in Florida during a hackathon. And I was making YouTube videos for like how to build on Solana. And some of those videos people still watch. Like I still get notifications about them. And I was like passing out business cards at the hackathon. Like, hey, if you guys are like looking to build on Solana, like here's my channel. And I was like shilling myself. And they hired me, which was pretty sweet. And so that was like my start at Solana. And then and I had already gone to the hacker houses and I was building on Solana, some cool stuff. And then I started working there and like building, like doing on-chain program work as like reference material and like doing like education and stuff like that. And then eventually made my way over to labs because like I was just doing enough on-chain work that they kind of knew that I knew the stuff. I knew the tech stack or the tech stack for like on-chain work. And I've been working in like an engineering capacity since then.
That's awesome. So, what do you focus on today at Anza? For example, when I saw at your GitHub, you have comments across a variety of repos, right? Like uh, Mollusk, Kodama, then into Akave and some of the core programs as well. So, what's your area of focus at Anza?
I'm kind of like I'm definitely spread across quite a few locations, but I tend to focus around like the realm of on-chain programs. So like I've written a lot of programs, I've worked on a lot of our programs, and then I've worked on a lot of like tooling that is focused on those programs, and also like the parts of the execution layer, which I know you guys want to talk about today, which I think will be sweet. So like a lot of stuff that has to do with just like deploying programs to Solana and like everything in between, right? So like to list a couple of things specifically, I worked a lot on like decoupling our SVM, which we call SVM. We can get into that as well, what's what. But the API that you would use to build like a network extension or a rollup. So like decoupling that, did some refactoring internal to those components as well to just help things run smoother. Worked on a lot of on-chain programs that we use internally or like other programs that like we've worked on for other people that like help them out and stuff. And then tooling like testing harnesses and yeah, I've contributed to things like Kodama and I don't think I have any commits on Pinocchio yet, but I got to change that soon. But yes, all kinds of stuff like that.
How do you even start defining SVM? Because when you look at the runtime, I guess it was called C level in the beginning, right? So it made the runtime makes up so many different things. It's the state, it's the storage, it's also the scheduling. How do you define first? How do you define what is SVM? Like, if you have to.
So technically speaking, the SVM is the state transition function of Solana. So like if you give me a set of inputs and you get a result, that the inputs are going to be accounts and input data. And then the result is going to be changes to that account state and some code, right? And there's like logs and whatever else. But the point is like that right there, that transition function is SVM. And like in the stack where that actually happens is technically like within the program runtime. So like the way that and a lot of people will like debate exactly what constitutes SVM or not, but the way that I envision it is like everything that is involved with like executing a batch of transactions, it all distills down to like what are the programs in your transaction? And there's obviously like usually many or multiple of them. And so for each one, there's going to be a stage that will load that program and execute it with the inputs that are in the transaction. And that right there, I think, is the SVM. That's the state transition function. That's where accounts actually change. Now, obviously, you can make an argument that like the transaction piece is like a necessary part because it's atomic. But technically, the way that it works in the actual runtime is all those changes do happen. It's just they get committed to the block later if the transaction is successful. But they still occurred. The state transition function still exists. So that's the way I define it. It's that transition between the inputs that you give a program and what the result is of it. And like everything else besides that is runtime or banking stage to be more proper. And like banking stage includes runtime.
Taking a step back, right? For example, for developers who are new to crypto or people who are coming from the EVM side of the world, how should they understand SVM? Because when you look at EVM, they have like a specific opcode. The virtual machine works in a specific way. So when we draw a parallel to SVM, what is the best way for them to understand what SVM is?
That's a good question. I mean, obviously the two are quite different, but we do have actually an instruction set architecture that lays out what all the opcodes of the VM are. We do have that. So if you want to look at like how the actual Solana virtual machine works, the one that is supposed to implement eBPF and is supposed to like execute your program, that one is defined. And the opcodes are all listed in the SBPF repo. As far as the other stuff goes, we don't do a great job of like speccing everything out. And that's like a product of like most of it having built like super quickly and like launching. And so it's taken us a long time to go back and actually like spec this stuff out. And maybe we should. But what's missing, I think, that like the difficult piece for EVM people coming over is like, what is the spec for basically everything above the VM, right? So like most EVM devs aren't used to like having to specify all the different accounts that are going to be involved in something, marking them as readable, writable, things like that. And that can be a little bit like verbose and annoying. And I think that's the cusp of where we're missing a lot of like specification. Is like how do these accounts actually get used into different in program executions? Like how does the like thread pool work that determines which can be like used in the same batch? And that has actually changed recently, because like previously a batch had to be non-conflicting. And so like if even one account was going to be written to, it needs to go in one batch and then like it needs to appear again in a later batch if it wants to be written to again. But now that doesn't do that anymore. So the spec would have changed recently again. So we're missing some specs in that area. Basically all the stuff that makes Solana like go burr with like the accounts being parallelizable, that's all like pretty underspec'd, I think.
You mentioned eBPF, right? Like a lot of the SVM execution environment is actually the eBPF, and then we have special opcodes on top of that. That's actually an interesting choice. Can you talk about why eBPF was chosen as the execution runtime versus something like Wasm?
I mean, the core reason that they picked eBPF, so there's a couple like main engineering focused reasons, and then there's also one that was like it was just easier to do. So like on the engineering side, it is like a known standard and a pretty performant way to do, like it was used in packet filtering and in networking. And so like it's a fast way to do like an ISA for like a VM for different kinds of sandboxed environments. And so it was really useful for the performance that you could get out of it and also for the sandboxing capabilities that the VM offered. So like you could have this like isolated architecture where like everything that happened is say is like self-contained. And that works great for like a blockchain because that way you know that like nothing that happens within this VM is going to like panic a validator, right? So that was huge. And the other thing that I was alluding to is like there was already an implementation in Rust available from this guy named Quentin, who we forked it from a long time ago. This is long before my time. And so that was probably a huge help already as well, is having something that you could build off of without having to start from scratch and things like that. Now I don't know what was maybe around or prevalent at the time as far as like something that could have been used instead. I know nowadays we've talked quite a bit about looking into Risk 5. I don't know if that's going to happen or not, but it's something that's maybe worth exploring because it's getting popularity. But I mean, to this day, like eBPF is still pretty quick. So unless like there's really a lot of like compelling reasons to switch it, I don't think the switching cost is really worth it. But we'll see.
Interesting. It's also interesting that you mentioned, supporting RISC-V, right? So is a part of the modular argument today is that so that you have the ability to upgrade some of these components independently. Yeah, I think it's also, we could also talk about why modular, right? Like why move from a monolithic integrated design into a modular, at least at the code base level.
But well, so like my take on this is like if you have like a lot of well decoupled components in a validator, it's like if you think about it, the validator is pretty big, right? So like there's actually a lot of stuff in there. And if you can decouple a lot of components in like a sensible way, not just like every little thing needs to be like its own isolated component, but at least sensible buckets of performance and functionality, you can actually have like a lot of plug and play for different validator clients. So imagine a world where like the labs client that we had for years is like this big like machine that runs all these different blocks of components, and somebody wants to like change one of them. They could just fork one component and they could change that one component and plug it in. And like this is what Jito does. But because they do that, like there is no like easy way for them to plug their changes in. So they have to maintain a fork and have done that for years. And sometimes it's not so bad. Sometimes it sucks because they have to like upstream all the cherry picks and like get all the changes from the client. And that's like not really a fun process for anyone to maintain like a fork or a mod or anything like that. So if you imagine the scenario I was like sort of laying up, if I'm like a node operator and I want to change like one or two components, I can easily do that. And then I can keep getting updated software as Anza releases new updates. And I just have to worry about like updating my piece, or like bringing in the features that have been added to that little piece. And so then you end up with like a network that has a really good spread of many different versions of many components. And so like a lot of people talk about the benefit of having someone like FireDancer or even Jito, like for the same reasons. Because like if there's a bug in Agave, for example, and hopefully it's not in the other client, then you have part of the network that can still run. You can apply the same concept to individual components. So like if you have a bug in one component and everybody's mod maybe doesn't have it, or like some mods have it, some mods don't, like you have actually a little bit more resilience that way as well, for the same reasons that you get it for having multiple clients. But obviously the main benefit, like that's a huge one too, but the main benefit is like you can do a lot more innovation on top of Agave without having to worry about like all this crazy coupled code that you're going to have to update every time there's changes to somewhere in the stack. And it's really a pain. So it would be nice. And it would, I mean, my like long shot idea is like if we did have that, you could have people like commit stuff back. I've said this many times before and it hasn't happened, but you could have people commit stuff back and be like, hey, I've been tinkering with this. Like I have this fork of whatever. Like I really think the protocol should just do this. or like the base validator should just do this, and you guys should like blah blah blah, and you make a case for it, and then suddenly it's maintained along with the like flagship validator, and then like you can push the cluster along with like new tech. So I don't know, there's a lot of benefits, I think, but it's mostly for people who just want to tinker around, man. You know?
Yeah. It's also interesting you mentioned that because it kind of drawing this clear interfaces and boundaries between different components kind of also, gives you the interfaces that actually become specs for these components. So in a way, it kind of starts documenting what these components are and how they're supposed to behave so that now it makes it much more easier for someone to build a new thing and potentially also upstream it if that is a good reason for it.
Absolutely. That would be awesome. That's ideal, because then you have like a well-defined interface, a spec, and then you know how to hook into it.
You mentioned different mods, right? I'm curious to double click on what type of mods are people running, or typically what, especially around these specific, which of these components are people actually modifying and why?
There's quite a few that people tend to mess with. So like you can mod things like Geyser if you want to like get more information extracted from your node. And you could have like different infrastructure that you have alongside of it. Maybe you have like some cloud databases or whatever. You're tracking different telemetry. You can also add more telemetry in general. But the most popular one for any operator to mod is going to be the block producing agent, like anything that has to do with producing a block. So, like basically your scheduler. And obviously, the reason is for MEV, right? You want to try your hand at ordering a block in a way that you think is going to be most profitable. And like some people just run Jito and they do like the auction method and they go through some of the like the mechanisms that they offer. And some people do it themselves. They have their own custom setup. And that's mostly what people do. And I think that that's not necessarily a bad thing. It's just that like it can be a little bit like Wild West. So one of the nice things is I think we're moving towards a future where like that's a little bit more decoupled, like we were just talking about. And so you have like a validator that is not so tightly wound with the different scheduler components. And you can actually like plug in more stuff in there. And then ideally the second step is like, here are some standards now that we know like external third party or just decoupled block producing in general is like no longer this like fringe forking thing. It's like a pluggable thing. Then you can start to have like standards. But yeah, I would say that anything block producing is obviously going to be the biggest one that people mod.
You also mentioned network extensions being like a use case for, having these components, right? So I'm curious to know like what is like the spectrum of changes this network extensions who don't necessarily sit within the main Solana network, but are kind of like extending the network, right? What kind of modifications do they make? Do people mess around with how the state is stored, for example, the accounts DB, or even maybe even possibly the runtime as well, right? If the SVM API doesn't like strictly enforce it being a SPPF shared object, it could be a risk by binary as well, right?
The different extensions that I know about that are true extensions and not like SVM L2s for like another base chain. Those, it seems to be common that people want to do like permissioned environments or like state channels. And like those are pretty like classic examples. But for those people who don't know, like a permission environment is obviously you're kind of like forking the Solana runtime, but you're still like compatible with all the primitives. However, you can add and omit some of the things that will still allow you to be consensus compatible. So, for example, let's say that I want to have like a side chain, but I don't want to do staking. So you just like create a fork and then you just don't have a stake program. Or maybe you want to do one where like you don't have token 22, right? Or there's like certain restrictions on token 22 extensions that are enforced at a protocol level. That's pretty easy to do as like an extension. And so there's quite legitimate use cases there too. And I think we'll see more with like some of the stablecoin legislation. But for now, I don't think there's too many extensions yet. So we'll probably see more.
How are people using SVM APIs to build state channels?
Well, you can build a state channel with the API without having to worry about any of the rest of the cluster. So you don't need to like fork a validator or spin up like a cluster to do just like simple payments. Or if you have like a well-defined standard of state transitions, you can really simplify everything. So like the classic one is going to be just transfers. So if you want to do just like sole transfers, like imagine you and I want to set up like we want to set up like a P2P network within our, let's say we have like an app or we're a bank. You can just like take the SVM API and you can like load account state from Solana that are like owned by your program. So like you don't have to worry about them like rugging underneath. And then you do all the payment processing on your little like extension layer. And then you settle it like periodically to the accounts that are on the base chain. And like you can see that first of all, you can probably make that a little bit faster. But the nice thing too is you can aggregate changes too. So you can say like, I'm going to keep track of just like the delta of everybody's balance and I'll do that settlement later. So it's like I don't need to post every like balance change to the main chain every time. And so you save on fees, right? So you don't have to tell Solana every time somebody makes a transfer. You just wait for like maybe like a minute or 2 minutes or an hour, whatever you want to do. And then you take the final ledger and you put that to the chain and you're going to save on fees, likely orders of magnitude. And then, like anyone, depending on what the app that they're running, you can easily sprinkle in some of the permission stuff we were talking about too. So it's like, oh, you can make these kind of payments. You got like payment limits, blah blah blah. But that's up to whoever is implementing that. But that's the most common way you could use a state channel. If you don't want to do just payments, though, you can do it in just about any kind of transition you want. The idea is you can make it hyper focused. So you could say like, here's a program that defines our like transition functions that this account can do and like the state channel can do. And then as long as you can still update those to the base chain, like your program on the base chain and on the extension are compatible or otherwise matching, you can do it with just about any kind of state transition function. The idea is you're not just like this all-encompassing any third-party software channel. You're a focused thing, but you use the same API, the same like primitives and everything as the base, and it's quite easy to rectify everything at the end.
That's awesome. And all of this is possible because of the refactoring you mentioned, right? And where all of these components were tightly coupled now, since you have decoupled them, you can take these pieces and, start using them in different contexts. I'm curious to know what was the most challenging part of decoupling, doing this refactor.
Definitely the bank. I don't know if you guys have looked at like the code in the bank, but it's a really, really big file. And it used to be even bigger. And I didn't actually start the refactoring. There was a couple of us working on it, and I jumped in later. And thankfully, a lot of that was like in flight already. So I just jumped in and started pulling stuff out of bank myself. But whoever started the effort originally, probably, I think it was this guy named Pankaj. He was probably the one who had to deal with the most, like, oh my God, where do I even start? Because that file used to be massive. It's still huge, but it used to be even bigger. So that one definitely sucked. It needs more refactoring, but nobody like has time to go take that on yet.
That's awesome. It's switching gears into Mollusk. It's like, why build Mollusk? Like, why is it important? Also, why would when does a dev choose, for their testing, why should they choose something like Mollusk over the Solana program test, which most, if anyone is already writing some of their tests in Rust, they're already familiar with, right? So what was the thought process behind Mollusk?
Well, basically, so it's a pretty versatile like test harness. So you can use it for a lot of different things. And we've actually seen a lot of people come up with pretty cool use cases besides what it was intended for. But the original idea was that we needed a good test harness that would let you write unit tests really easily. And the problem with things like program test was that it just brought with it so many things that you just like really didn't need. And so it would bring with you like a bank, like I was just talking about how big the bank file is, like the bank itself is quite large. And so it does a lot of stuff. So it'd bring like the runtime. And if you're testing a program and like if you're doing unit tests, you really want to test one case on one instruction at a time. And each test is a different case, and like each test suite is a different instruction. At least that's the pattern that I think most people should follow. I mean, ultimately, devs could do whatever they want, but like that's my suggestion. And that was how we were writing tests, but it was really like verbose and annoying. And then we would also get a lot of problems as our test suites grew because like if you spin up too many program test instances, you end up with like timeouts. And so I wrote this thing that basically just says, all right, give me the accounts and the instruction data, and I'll just invoke the program on the VM, and that's it. So like I won't bring any of the bank or the stakes cache or any of the other stuff that like you don't really need. And I won't even persist the account changes. I'll just give you, like we talked about the state transition function, the SVM, like STF. That's all it is. It's just the transition function. And so you can test exactly what you're trying to see from the VM, like from the program using this harness. And I will say that like most people, I think have found that quite useful. Some people get a little bit tripped up here and there sometimes because it can be a little bit like explicit, but that's kind of the point. And I've added some features over time to make that like less of an obstacle when people are trying to get onboarded to it. So there is like a persistent account store and there's stuff like that if you wanted to expand on some of the writing. But the core like tenet of the harness itself was like each test is one case of one instruction, and you just do like you spin up a Mollusk instance and then you just like invoke it. And you can also like keep a Mollusk instance around and like keep invoking it too. And so there's like other goodies in there too. Like you can record and benchmark your compute units and stuff like that. But that was the motivation. And so far so good. I mean, we use it all over the place. And I think it works well for that intended use case.
Interesting. So the idea is that Mollusk actually shaves off all the expensive setup and teardown times. For example, if I were to set up an entire bank's client for every unit test case that I have to run, ends up adding a lot of time. So Mollusk makes it much more faster. So now I could actually run it on GitHub CI. Is that the
Yeah, it's a lot less resource intensive for sure. The other nice thing too is like I'm obviously a little biased, but I think that some of the setup is a little bit more like customizable. So like when you're working with like program tests and you have like a bank in there that you need to work with, you have to be careful when you do certain updates. So like some of these things were just bugs that we just could have maybe gone and fixed, but like a number of things I would run into was you would need to set up some accounts and you would want to test with these accounts. And so you have two options. You can either set them all up ahead of time and then like run your tests with transactions. And if you need to change anything in between or like look at some intermediate state or whatever, like you have to be careful about when the bank is frozen, like things like that, if you need to advance the slot. And so it was a little bit tricky to work with those kinds of things to manipulate the environment on the fly. And the other thing that was difficult to do was like setting up sysvars and just things like that were not like super simple. Not impossible, but not super simple. I think that that's a little bit easier to do now too.
And another pattern that I have noticed is that people directly use anchor tests, like they write their program in Anchor and then Anchor creates this Mocha test for you and they use the ideal to test against. So what is what is the best, since you have built a lot of on-chain programs, like what's the best practice that people should adopt, especially when it comes to testing? Should they test it via their ideal, or should they just directly have their test cases at the program level in Rust?
I don't know. I think you're asking like where should you write them?
Yeah. I mean, for on one practice, what I'm asking is what's the best pattern? Should people write their test cases? For example, if you're developing in Anchor by default creates this test folder, and inside it you could have your entire test suite and written in Mocha, right? So the question that I'm asking is like, how does something lightweight, very fast like Mollusk benefit them? Because that actually ends up spinning up like a test validator, deploys programs to it, and then executes all your test cases against one state of the validator, right?
So the way I would do it, the way I would recommend is like if it was me, I don't write a lot of Anchor programs anymore, but if I was writing Anchor right now, I would probably write a whole like suite of unit tests in like, so I would have like program source, right? Like my program code, and then like program tests. And in program/tests, I would write a slew of unit tests for each instruction. And I actually like, this is what I do right now. And so like if you have, let's say like 3 processors and like 3 instructions, like you usually have 3 files. If you write it all in one file, I mean, maybe that's your jam, but like usually people will split them into like 3 different files. And so then you just have like 3 different test files. And like, again, this is like just what I would do. I'm not saying anyone has to like get this granular or anything, but you have each one mapped to an instruction and then like go down the line, and each like test attribute function should cover like a different edge case or a different case in general that your program is checking for. So with Anchor, this is actually a little bit not obvious to test because the framework does a lot of things for you. And when like you can configure the context to do a lot of these like checks and assertions. And so you can test it and make sure that the framework is going to do what you expect. It's probably a good thing to do. But it's not always super apparent. Like when you write something in native, you actually put the check there yourself. So like you know what to look for. And so I just go down the line of like the program control flow, like the logic, and just start at the top. Like, what is the first check that I see? And it's usually like this person is a signer. Okay, first test is going to be like fail, this thing isn't a signer. And then you set up a Mollusk unit test and you make sure you get the error code that you're looking for. And you just go down the line. And then outside of the program source, like the program source and test folders, what I would do is I would use the Anchor like boilerplate setup and the client to do an end-to-end test with the test validator. And the reason that I would do it like this is because with the test validator, it's really good to get like a gut check that you can start from zero and like go through the whole like end-to-end flow and nothing like craps out in between. But when you're trying to make sure that certain things fail, it's actually better to have like really quick fire unit tests that do one simple thing. So then all your unit tests cover all the failure cases, and maybe you have a success case in there too, but they cover all your cases. And then your end to end is just like, does it do the thing that I built this thing to do? And like, then you just worry about that. And I think that's probably the optimal way to do it. But like I said, anybody is free to do testing and development however they want. That's just my jam.
I think one key distinction here is that the Anchor, whatever tests you write in Anchor, those are more integration tests because you're operating on one specific state of the validator, and then you're, keeping up, continue to make changes. The interesting part about Mollusk is that now I can actually use it with a property testing module like quick check. Now I can exhaustively test different corner cases, right? So yeah, it's super interesting. I'm definitely going to use Mollusk with quick check now.
Nice. Yeah, I haven't tried that yet, but it should work just as you said. I have used it for like benchmarks because I wrote like a little compute unit benchmarker, and it's nothing really fancy. All it does is just read the final resulting compute unit value, but it will make a little markdown file for you. And so if you look at some of the core programs that are in like the Solana program organization, like a bunch of the ones that Anza maintains, like the lookup table, like those have a benchmarks folder. It's just called benches, I think. And in it is a markdown file. And I've said this multiple times, but I stole this from Anchor. I took this idea from them. They will benchmark all the CU usage of like different APIs and types with new releases. I thought that was super cool. So I put this in as a feature, and you can like do it on a program. So if you like make a change to dependencies or to anything in your code, you can see the change to the CUs based on your benchmarks. And so that's been pretty neat. But yeah, that was all Anchor's idea.
Awesome.
I just had a question. Do you have any specific repositories that you recommend people look at when you have both these set of tests on the Rust side and on the client? Is there any specific repo which has them well documented so people can actually look at it after the pod?
I would say the Solana program org has a lot of really good unit test examples, but we don't have a lot of good examples of testing with clients because like we don't really use Anchor at Anza. So I don't have any good examples of that. I would check out Blue Shift though. They definitely do. But other teams too as well probably have good examples, but we don't use a lot of Anchor.
Got it. Makes sense. And when you don't use Anchor, you don't ever at all write end-to-end tests with a client. They're all written in Rust.
I have written end-to-end tests in native Rust. It's just like I haven't done it in like our stuff. I've done it in other stuff that I've helped other people with that I can't really share. Yeah. But for our stuff, no. We have some, like there's some end-to-end tests with like CLIs and whatnot, but I wouldn't recommend those as being like good examples. Some of them are like really verbose or they're like ported over from old tests. I don't know. I think there's probably better stuff out there.
What is the most quote unquote elegant hack you've seen in the Agave code base? Like it probably shouldn't work, but it does.
I would say probably the craziest was what was like, I think feature activations are pretty wild. So like the way that it kind of works is you have like the epic rollover phase where like an epic ends at the end of some slot, and then the next slot is the first slot of the next epic. And in that transition, like between every slot, there's a process of like one bank becomes a new bank. So like imagine like a bank maps to a block. Pretty much they do. It's more complex than that, but you can think about that for the analogy. And so like each slot, you get a new bank that's made from the old one. And then in the one that's on the epic boundary, like a million things happen. And we've been trying to like thin that out, like what happens there, because it's like obviously a big like compute job. But the feature activations in particular, I think are interesting because it's like they all happen at once. I mean, we only activate maybe one or two at a time, but they are all right there on that boundary, and they're activated, and then they are like piped through all the source code. So like to give you an example, like if you activate a feature, you submit an account, like you submit a transaction to put an account on chain under a certain owner, and the key is in the software, like the pub key is in the software. And so once that account exists, during the epic transition, the runtime sees it and it activates that logic gate. And so it's kind of clever, but it's also like crazy because it's like you have this hard coded address of an account that doesn't exist. Then somebody creates it and causes this action to occur on a live cluster during an epic transition. And so there's a bunch of reasons why I think it's like an elegant hack. Because like a reason I think it's elegant is I think it's like a really good idea and it's clever. But the reason I think it's a kind of a hack is because it's like it like flips basically a logic gate all across the entire validator, but on all validators that do it.
So it's kind of like a crank, but instead of someone externally triggering it, you have it as part of the code base.
I mean, I don't know a better alternative to like activate a feature on a cluster that needs to all do the same thing at the same time. So I think it does make sense. But when I first figured out how they work, I was kind of mind blown. And you can go look at these in the code. Like if you go through bank, there's a like a part of the code that says like new feature activations. And so what it will do is like on that boundary, it will look up all these pub keys and see which ones exist that didn't last epic. And it comes up with this short list of like these we just found. Like we just found these ones now. So we got to go do something with these. And then it'll go through that short list and turn them all to true. And like there's logic that is like basically hooked into these for like the first time they become active. And so like the way the features actually work is there's like two ways. So like one is like there's an action that happens as soon as it is activated and that doesn't happen again. But then there's also features that like once they're active, like this path is taken instead of this one. And then you eventually never go back to this one. So it is clever. It makes sense. It's just like when you see the code that does it though, you're like, whoa, this is kind of like wild. It's just like it recognizes an account all of a sudden randomly that like just appears, and then it just changes the behavior of the validator. But it's pretty cool, I think.
Okay, one more question. What are your thoughts on Cindy 215?
I did try. I mean, dude, like I'm a light client guy. Like I understand why people want them and need them, and like I'm all for it. But ultimately, at the end of the day, like most of the Anza devs are trying to make the cluster faster. And unless enough people like stand up and say like, here's this thing I'm building and I need light clients, like they're like we're gonna probably make compromises that make the chain faster. And that's exactly what happened with 215. I mean, you could argue whether or not there was enough discussion on it. I don't really know. I would just, what I'm trying to say is like, if enough people think that it really stinks that we don't have good light client support and it's something that we need to fix, then we can do it. Like no one's against it. But until this day, like there really hasn't been a ton. There's some, like there's definitely some teams that have pushed this idea forward, but it's not like this giant outpouring of projects. If that was to happen, if a lot of people were like, "Hey, this is like really kind of terrible that we don't have support for this," I think that would change the game. Because like I understand you want to have like trustless bridging and you don't want to have to do all these like weird things. And some of the guys that have figured out how to do proving, like it's very difficult. Like you have to, there's really no way around. Like someone has to run a modded node if you want to have anything that you can use to do proofs. And then you're kind of like trusting this fork. And so it's not ideal. So I'm all in favor of light clients, but I also think that like unless somebody is like, hey, let's not make the chain faster because we need this light client and here's why, and it's a compelling reason, then like they're probably like the chain is probably just going to get faster. Like to be honest with you. But I'm totally on board. If somebody wants to like propose something or jam on it, I'm on board. We talked a little bit in some discussions on the SIMD repo, but yeah, I don't know. I think the idea has just fallen a little bit flat sometimes, to be honest.
That's awesome. We are towards the end of the pod, so just have one more question. What is one feature that you're most excited about in SVM? What is that one thing that keeps you up at night?
It's a good question. I think so. There's some things that keep me up at night for the wrong reasons, but I think that I think the async program execution sounds pretty cool, and it's an interesting problem to try to solve because for anybody who's like seen some of the discussion about it, there's like this concept of like execution domains. So like if you think about the thread pool concept of like Solana's sea level, and you know how like if an account is writable, right? Like you have to make sure that nobody else is trying to write to it at the same time, like basic thread lock stuff. But then you take that same concept and you say like, okay, how do you set this up so that like different kinds of transactions, like different kinds of execution flows can happen at the same time, and we can isolate different types of accounts from each other. And like Anatoly has a good paper on this that I don't know if it like kicked things off or he just kind of jumped into the mix when people were already talking about this, but he talks about first like the voting domain versus the rest of the cluster is like a good way to conceptualize this. So if you think about like votes, there's really no need that you would require like a vote account to be writable unless you're voting, right? So if I'm voting, I know that the vote account is probably going to be writable. Maybe not, but usually. And so that's something that can happen in vote land, right? But then something else that's like a token transfer has nothing to do with vote land. Like these are two separate worlds. So if you have that as like a primitive in the chain, that makes sense. And you can build on that concept and you can try to isolate different domains of accounts that would be used together. And like, dude, you can profile blocks and figure this out. Like, you can look at what dexes use. Like, all this stuff is related. Like you don't have some random protocol that Joe Blow wrote that you include accounts from in your like drift transaction. Just this doesn't happen. So there you go. Like, you have separation that you can do, and then you can parallelize more stuff, and you can have like pipelined approaches to things that like you can basically just have like super fast, some stuff that's super fast. And like Hyperliquid did this. And they did this for like some of their DEX stuff. Like, don't ask me, I'm not an expert about all the things Hyperliquid, but reading some of their docs, that's how they accomplished some of their perf stuff, is they did some pipelining around like transaction, whatever, like transaction domains. And Sui did this too. So Solana did this, we would probably squeeze out a ton of performance with this. And I think that that's a really cool idea. That would probably be great for the chain. And with Alpenglow, I think I'm not entirely sure if it's like directly affected or not. I'd have to think about it quite a bit, but I think that like combined, those are really good features to have for performance. You know,
Thank you so much for joining us, Joe. Been fantastic having you.
it was great chatting with you guys. Hopefully it was interesting for some of the devs out there. And yeah, if anybody's ever curious about anything, whatever, you can like tag me on Twitter or like find me on Discord or Telegram or whatever. Maybe we could share some of the handles in like the description or whatever. But yeah, happy to jam with anybody who's down.
Thank you.
All right, see you.